Good afternoon, everybody. Welcome to this webinar on moving beyond uncertainties and rethinking climate models. And we are just waiting for more people. We are just waiting while a lot of people are joining us. And we'll start in a minute or two when the participant numbers saturate a little bit. Now we've reached 100, so we might as well start. I'm sure there will be still people joining us. So welcome everybody to the 29th webinar in this discussion series on tipping elements and tipping points. My name is Gabi Hegal. I'm a professor at the University of Edinburgh, and I will moderate this session. And we have two exciting guests, which I'll introduce when they before their talk. But it's basically David Steinforth and Thomas Stocker. And the goal of this series is to advance knowledge on tipping elements and tipping points in order to improve consistency of how we deal with this topic in the scientific community and how to develop a research agenda on this topic. And also the seminar series also contributes to the design of the TIP-MIP tipping point into comparison project. So there's a number of networks that support this webinar series. That one of them is the Earth Commission, the AIMS, the Analysis, Integration and Modeling of the Earth System project. And both are hosted by Future Earth. So Future Earth has a big role in enabling this webinar series. And it's also supported by the Safe Landing Climate's Lighthouse activity of the World Climate Research Program, which I co-lead. And this this event is co-organized by the International Institute for Applied Systems Analysis, the Potsdam Institute for Climate Impact Research, and the Global Systems Institute at the University of Exeter. So I see the numbers are still increasing, which is great. There's one fundamental thing to consider for the audience, please. If you have a question, and you can ask questions anytime during the talks, put them into the question and answer box. So you can see below in your taskbar that you have a question and answer box and a chat. And please do not put questions in the chat, but put them into the question and answer box. The audience can also upvote questions that they find particularly interesting and would like to see answered. And we will try to get through as many of your questions as possible. And the way this works is that we have first the two exciting presentations, and then we have a question and answer sessions to both panelists together to address your questions. Okay, how are we doing on? Numbers are still going up, but we are almost at the number of registered participants, I think. So maybe I'll start with introducing Dave. Should we do that? So the first speaker today is David Steinforth. He's Professor David Steinforth is an expert on uncertainty, analysis, and climate change. He is based at the London School of Economics and has a BA in physics and a PhD in physics from Oxford University. The title of his thesis was Uncertainty and Confidence in Predictions of Climate Change. So David has challenged the climate community on this topic through his career, and I'm looking forward to his talk today. He's also written recently a book on this topic, Predicting Our Climate Future, which is available from Oxford University Press. So yeah, thank you very much for coming, David. And would you like to start?
Yeah. Thanks very much, Gabi. Let me share my slides. So is that right? Is that full screen?
This is now full screen. Great.
Good, super. So thanks very much, Gabi, and thanks Caroline for organising this event and the whole event series. So as Gabi said, I've been interested in trying to think about uncertainties in climate projections for 25 years now. I think when we start to think about uncertainties in climate projections, the obvious starting point is from a physics starting point, from the physics of the climate system, what we understand about atmospheric processes, ocean processes, land surface, ecosystems, cryosphere. And and how we model those processes. And I think that tends perhaps to dominate our assessments of uncertainties. But when I started getting into this with work on perturbed physics ensembles back in the early 2000s, what that raised for me was the fact that there were a whole load of other subjects and other issues that came to play when you think about climate projections. There is, of course, nonlinear dynamical systems aspects, not just in terms of the geophysics, but also in terms of what a model represents. There are issues of stochastic processes and memory, long-range memory within the climate system, and how that plays out within the maths of stochastic systems. But then there's also issues of epistemology, of the philosophy of science and the philosophy of climate science, which perhaps beholds that we should be asking deep questions about what are the foundations for the knowledge we have about future climate. And for me, that took me on to discussions with economists, with the financial sector, with consultants, with policymakers, which I think also comes to play when we think about climate projections. This isn't a unidirectional piece of research work. It's not a matter that we do this research within the physics community or the scientific community and then hand it over to economists and social scientists. That's just not working very well. There needs to be much more throughput coming the other way of quite what is the most valuable piece of information, what the most useful information on uncertainties is. So I think when we think about climate projections and uncertainties in climate projections, a whole vast range of disciplines and subject areas come into play. And that's really why I spent my time writing the book that Gabby mentioned, because it's about trying to draw all these different threads together and identify how they connect and show that if you just pick one, if you're just looking at one at a time, then you're going to miss fundamental and really quite deep foundational aspects of what we are aiming to know and what we need to know. But the book is 356 pages long and the talk is meant to be 20 to 25 minutes. So the other aspect of writing the book was that there's that background information so that when you pick out certain themes, the whole rest of the context is kind of available. And I do want to pick out just 2 or 3 elements of issues that are dealt with in my book, but also that I tend to talk about more widely. And I kind of wanted to start by thinking about so what I see as 2 really foundational conceptual issues for climate modelers, which I don't think these issues I don't think have really been addressed properly or thoroughly within the climate modeling or the climate research community. And the first is, when is a model good enough? And the second is, when is a model, how unrealistic does a model have to be uninformative? I don't know about you, but my screen, the Zoom thing is covering part of my screen. So I'm just going to make sure that I can look at the whole thing. Okay, so when I put those 2 questions, those are the quick summary questions, but of course we require more details. It has to be a little bit more elaborate than that. When I say, when is a model good enough? What I'm talking about there is, when is a model sufficiently realistic to produce probabilistically predict how climate will play out on multi-decadal timescales and local or regional spatial scales. All of this conditioned on some policy choices. So that will be some scenarios of emissions or the like. And the other question, how unrealistic does a model have to be uninformative? That's really saying, when is a model too unrealistic to be informative about how climate change could play out on multi-decadal timescales and local, regional, spatial scales, conditioned on policy choices. So the crucial issues here is that we're talking multi-decadal to centennial timescales, and we talk about local and regional spatial scales. Even when we're thinking about tipping points, something large like ice sheet collapse or AMOC collapse, if we're trying to engage the wider society, if we're trying to engage policymakers, if we really think that society needs to significantly change the way it behaves, then we need to engage electorates, we need to engage populations. And that means talking about how climate tipping points and how climate change will impact them. So local and regional spatial scales become really important. And all of these are conditioned on policy choices. And let me come back to that in a moment, because because to my mind, and what I discuss somewhat in my book, is that there are a whole series of different characteristics that frame the study of climate change. But the first one is simply that it is all about prediction. We have, or we think we have, some understanding of what the world will look like in 50 or 70 years' time, if we, for instance, achieve net zero by global net zero by 2050, and we have, or we think we have, some understanding of what the world will look like if we only achieve global net zero by 2100. And that gives us two different pictures of the future. Conditional predictions, which we might call projections. And it's these different views of the future that give us a choice. Which one do we want? How much are we willing to spend to get it? Or how are we willing to change our judgment of what we value and shift our behavior in the light of these choices that we have? And it's the physical science of climate change and indeed the connections through to the economics that give us these predictions. So to my mind, the study of climate change in whatever subject you're working in is fundamentally about prediction. So how do we go about that prediction? Well, one approach is to use the type of the storylines or narratives approach, which has gained traction in recent years. And the idea here would be to say, well, use our imagination, but constrained by physical understanding to provide a range of credible futures. I think there's a lot more need for imagination in our work on climate change, but it has to be constrained by physical understanding. So it's not, we can't have anything goes, but we do want to use our understanding of the climate system and different elements of the climate system and tipping points in the climate system to explore and imagine how things might change in the future. It's one way of producing predictions. And the images here come from a couple of papers. Perhaps one of the starting points of papers on storylines was led by Wilke Haselager. Since then, there's been a lot of use of narratives, which has been really just a matter of interpreting what models say. But certainly what Wilke and I and colleagues had in the 2015 paper was very much more the idea that you would draw up pictures of what the future could be based on physical understanding, and then only use models to fill in the details. And the image here shows some work that I did with Suraj Desai led, where we were looking at what could be the changes in rainfall in southern India. And we were looking at the Indian summer monsoon, and we got a number of experts in the summer monsoon together, and we said, well, how do you think the Indian summer monsoon could change? And what they did was they said, well, this is what our models show. And we took us several hours to get onto a page where they wouldn't just tell us what the models show, but actually start thinking about what are the physical constraints, how could the models be wrong? And they came up with various ways in which the models could be wrong and that there are different plausible futures. So that's one way. We can look at storylines or narratives. That's not the usual way. The usual way would be the other approach, which would be to use global climate or Earth system models. So these things, I suspect most of you are very familiar with. I'm guessing quite who is here today, but I expect most of you are familiar with these, where we'll have some sort of breakdown of the atmosphere and the oceans into discretized blocks. We can represent our understanding of the Navier-Stokes equations of movements in the atmosphere and the oceans, and we couple those through to land surface process models and cryosphere models and ice sheet models, and we have a large complex system, and we use that to tell us about the future. Okay, that sounds great, and that's a very attractive route, which has been the mainstay of climate predictions for the last 30 years or so. But But there are issues here. Climate prediction, conditional climate predictions conditioned on some scenarios, is an extrapolatory problem. And we need to always remember that. We are taking the system from one state, and we're pushing, what climate change is doing is it's pushing it into a whole different state. That means we have no possibility of verification. This is entirely different to weather forecasting or finance forecasting. We have no possibility of making predictions and then seeing whether they are robust predictions of the future, because we're driving the system into a different state. We have no observations of what the climate will be like in 2070. And even if we did, we would only have one by the time we get there, which is insufficient for a probabilistic assessment. So that's one point. We have no possibility of verification. But more than that, when we look at historic observations, consistency with historic observations may be necessary for an adequate model, but it's certainly not sufficient, because the behavior of the system in the past, we expect to be different to the behavior of the system in the future. What I mean by that is what fundamentally human-induced climate change is driving the climate system from one attractor to another. You can imagine pre-industrial climate as being represented by one attractor, perhaps illustrated by the blue attractor in this diagram. But what climate change is doing is driving the system towards another attractor. We have no observations of this other attractor, and indeed what we're trying to do in climate predictions or climate projections is to try and give a description of how the climate system will behave as it moves from one to the attractor. But what we have is observations on one attractor. That's not going to tell us about processes that change in the future, and tipping points are a particularly good example of that. So consistency with observations may be necessary, but is certainly not sufficient. And I emphasize that maybe we don't even require that, and that's something that we might want to come back to and discuss at the end. Okay. The other thing about our models at the moment, we might think that consistency with the past observations may be necessary, but we need to accept the fact that all our current models are substantially inconsistent with observations. This is not really a dig at models. Our models are fantastic tools. They're fantastic achievements. But if we're trying to use them as prediction engines of predictions of 50 or 100 years' time, then we need to reflect on the fact that they are all substantially inconsistent with the observations. These are the CMIP6 simulations from the CMIP6 ensemble. On the left, we have global average temperature, on the right, Central European temperature, and the black line on the left is observations. You can see the variability within any single trajectory. You can see the variability within individual models. Individual models are colored the same. But you can also see that they are wildly different to observations, or on the right-hand side, any of them are going to be wildly different from any others, simply because you can see the variability in them. We're soon talking about ranges of temperatures of 3 degrees or 6 degrees here. What this is saying is that if you have this sort of range of temperature over a region between different models, then either they're going to get the surface processes, the land-sea interactions, the ecosystems wrong in those regions, in which case they're not going to be suited to provide us with the details of future climate at regional scales, which is what society is looking for, or they're going to represent, or they're going to seemingly be fairly consistent with observations in ecosystems and land atmosphere ocean processes, in which case those processes are ill-tuned because they're getting the right answer in the past, but they have to be for the wrong reasons because we're getting the basic climate wrong. So we just need to remember that however powerful our tools, models are, they are inconsistent with observations. So what do we do? Given those contexts, what do we do? Well, one option is to make our models better. And that, of course, is something that a lot of people are talking about. The several people in Hamburg and people in Oxford are very strong proponents of the idea that we should make our models better. We should achieve high resolution models. These are the sort of things that are discussed with the Earth virtualization engines, and calls are made for billions of euros to be put into this idea of making our models better. The argument tends to be that there needs to be a focus on better resolving atmospheric processes, but the atmosphere is only one part of the climate system. If we're going to make our models better, then we're going to have to make it all better. All our ocean processes, all our cryospheric processes, all our land surface processes. And that raises the question, when is the model good enough as a prediction engine for climate? Not necessarily as a tool for understanding climate, though already fantastic tools for understanding climate, but as a tool for prediction, when is a model good enough? And that raises questions about how close a model needs to be to reality to be able to make such projections. And as ever, when I put together a talk, I'm always fearful of not having quite enough to say. So I included some slides about the hawk moth effect, which I'm not going to have time to show. But the idea of the hawk moth effect is that it is quite possible that even the smallest errors in a model could lead to substantial errors in probabilistic predictions with that model. I don't have time to go through that now, but that's the idea of the hawk moth effect. It's beginning to be researched. It's just beginning to be researched in a number of areas. But there is a suggestion that you might be able to have a model that is really very, very close to reality, that is not identical to reality and will still make seriously flawed probabilistic predictions as you're moving from one attractor to another. So what do we do? Option 2, if making our models isn't the way forward, what else can we do? Well, one thing we can do is we can simply explore what our models can do. And this is the essence of the perturbed physics ensemble, the sort of thing that climprediction.net started doing around 2003, 2004. And what I'm showing here are some results from climprediction.net, where you change the parameters within the model and see what it's doing. And in this case, I'm looking at Northern European summer in response to doubling carbon dioxide in the atmosphere. I'm showing change in temperature versus change in precipitation. And you can see a whole range of different behavior from different model versions. There are questions about what these mean, really interesting questions about what these mean. Certainly, the fact that you have lots of clustering doesn't mean that that's more likely in reality, because all our models are different, so substantially different to reality, and we don't really have a metric for even the shape of model space. So we don't know that we're exploring it in anything like an independent fashion. So what do? Well, we have this simply a domain of behavior, and our aim should be to expand that domain of behavior. We should be pushing out those bounds. We should be looking for models that do things that no other models do. And when we find that we can't create models that show certain behavior, like cooling in response to increasing greenhouse gases, this lends extra evidence. It's a new line of evidence for what the real world can and can't do. But that raises the question of, well, okay, we can push out our bounds, but why can't we constrain it more? How do we pull it in? How do we say that some models are too unlikely to be realistic? This is a problem because all our models are substantially inconsistent with reality. So how do we identify that some are so much more inconsistent with reality so as to be implausible? That is a really deep question that we haven't begun to address properly. And I was going to say something about the problems of in-sample analysis in that as well, but I don't want to tap in on Thomas's time. So option 3 is simply that we throw away our models as direct route to predictions. We don't throw them away entirely, but we use them wisely to better understand interacting climatic processes and build and elaborate storylines. So we use them as tools for research, but we don't use them as tools for prediction. So that leaves us with 3 options: make a model better, explore what our models can do, or throw away our models as direct routes to predictions, but use them to build storylines. Option one and two raise foundational questions in climate science. Option one raises that question of when is a model good enough? Until we've answered that question, until we've really embraced that question, we certainly shouldn't be throwing billions at simply making our models high resolution and better. Option two requires us to embrace the question, well, how unrealistic does a model have to be uninformative? But that's not quite so urgent, because actually pushing out the bounds of behavior in our models is still valuable even before we have answered that question. And I would argue that options 2 and 3 are better direct routes to informing policy. And I think I'm just about within 25 minutes. I'm going to stop there, hand over to Gabby and Thomas, and I look forward to debating these issues today and hopefully in the future. Do get in touch with me whenever you like. Thanks. I need to stop sharing.
Thank you, David. Thanks for this very interesting talk that challenges our thinking. And we go to Thomas's talk now. Before we do questions and answers for everybody. Again, I can see that some questions are popping up in the question box. Please put them there as they come along. And the next speaker is, we are pleased to have Thomas Stocker, who is a professor emeritus at the University of Bern in Switzerland. From 1993 to 2024, he led the division of climate and environmental physics there, and also served as a co-chair of the IPCC Working Group 1 in the fifth assessment report. In his own research, he worked on tipping points and abrupt climate changes, and particularly in glacial interglacial cycle and future projections, and led this contribution to bringing back the CO2 level observations 800,000 years, and I think even further than that, using an Antarctic ice core. And he has also been championing the proposal for an IPCC special point report on tipping points in AR7, which is not strictly happening, but there are alternatives that we all hope for are happening. So, Thomas, the floor is yours.
Thank you very much. I hope you can hear me, and thank you for the kind invitation. Welcome everybody, and also thanks to David for a great intro to with some fundamental questions, which we hopefully will address then in Q&A. So the title of my talk and short presentation, is How to Approach Consensus on Climate Tipping Point and Why It Is Important. And the title already implies that I feel personally, and I think that's shared by many of our colleagues, that there is no consensus on climate tipping points. And with climate tipping points, I'm not only referring to the tipping points in the strictest sense and in a mathematical sense, but in a wider sense in which we're looking at out-of-scale extreme events as well, and impacts and surprises. Tipping point, surprises, high impact, low likelihood events. These are all keywords that float around in the climate science community, and their effect is really stunning. They usually garner a high level of attention by the public and by policymakers. They are often used to express urgency for climate action. And in my view, they also have some potential to divide the climate science community. I would call them some of the those who propose that everything is a tipping point or involves a tipping point, the tippists, and other members of the community with equally strong arguments would say, well, the climate system is so damned and so resilient that everything is to first order linear, and that would be the linearists. And obviously this doesn't sound like a consensus, and yet consensus is so important in the climate science community to reach the next level. What has happened in the past is that tipping points and surprises have been really taken up also in assessments, in vulgarizations, in overview papers, such as, for instance, in the 2022 edition of the United in Science brochure issued by the World Meteorological Organization, or a substantial report that was published just before the last COP on global tipping points. Also, the policymakers are chiefly interested in the topic. Here is an excerpt of an informal document from the 60th plenary of the IPCC that took place earlier in 2024. The delegates were asked what are the most important points that you would like to have assessed in the 7th assessment report cycle were you to choose a special report, and out come this list here with tipping points as by far the leading topic of interest. 18 countries have put that at the top. Climate change, adaptation goals, adaptation metrics comes in second, and a topic of a previous COP, loss and damage, only came third to be addressed as an assessment piece of work for the 7th assessment cycle. So the interest is very high, and I would argue that a scientific assessment, due to the long process and the multiple stages of review, would facilitate a consensus and at the same time accelerate our understanding. As Gabi already mentioned, there was a proposal, incidentally by Switzerland, to the 7th assessment cycle for a special report on tipping points. It was as unsuccessful as any other proposal, and there were many topics of interest since the leadership of IPCC of AR7 has decided not to commission any additional special report to that has already been decided in the previous cycle, and that is a special report on climate change and cities. So it is a highly relevant, policy relevant topic that needs to be assessed, clearly not only in Working Group 1 on the physical science basis, but I feel across all 3 working groups, from impacts also to mitigation. What has happened in the last plenary is that at least the IPCC considers an expert meeting in 2025 on high impact events and tipping points. You can see here already that the perspective has been widened up, which I think is a good thing. But note the word consider. For those of us who have been involved in IPCC, they know quite precisely what that means. The IPCC considers, I would put 3 question marks here. Considering doesn't mean action necessarily. And so I think we need to be alerted to the fact that if we want tipping points to be a focus, and if we want to advance the consensus in that area, we need to take action. One of the next milestones where action could be taken, and if I see the high number of participants on this Zoom call, I would argue that a great opportunity is the forthcoming scoping meeting on December 9 to 13, which will be taking place, organized by IPCC, where the table of contents of the 3 working group contributions will be discussed, negotiated, and decided. That's where you could put in your proposals, for example, a chapter on tipping points and high impact, low likelihood events. And I will come to that towards the end of the presentation. We all know what we are talking about. There are global scale tipping points, such as the disintegration of parts of the polar ice sheets or the Atlantic meridional overturning. But I think much more important, and also much more interesting and much less understood and researched, are tipping points that have a strong regional impact. That is, tipping points that would be felt by people and ecosystems. And I've highlighted these in red. For example, the Amazon rainforest, all the monsoon systems around the world, which provide resources for people directly. If there is tipping in any of these elements, the impact will be extremely high. And so, just as an example, the Atlantic meridional overturning circulation, something that has been researched for several decades, also addressed already in the first assessment report of the IPCC, but still not a consensus is available here. For example, the figure out of chapter 4 in AR6, so you can see the model simulations. They pretty clearly show a picture of reducing AMOC over the 21st century, but with large uncertainties here, as you can see in the colored clouds. Another very interesting, much more recent result is a simulation by Natasa Romanu from the NASA GIS using one single model and exploring slight changes, the effect of slight changes in initial condition. And you can see here that predictability, even of that large-scale phenomenon, is a big issue. Some of these simulations in the 22nd century recover to normal overturning that we had before. But there is also a possible bifurcation where you see that 2 out of the 9 members of simulations here show a permanent slowdown of the AMOC, that is an irreversible change. So whether or not this system changes irreversibly, that is still an open question, and we should not be fooling ourselves in looking at multi-model means here for this specific question to come to a consensus. Multimodal means are excellent tools for large-scale processes, but when it comes to extreme events or tipping points or hill events, individual simulations need to be considered. But also observations come online which question our understanding. For example, whether we are able to actually understand the temporal changes of the Florida current, a very recent result that brings in the slow changes of the Earth's magnetic field in modifying these results of that circulation, the southern part of the global conveyor belt in the Atlantic Ocean. We then look at the shortcomings of models, and here I pick up an issue that David was addressing in his option 1. These models, certainly what the ocean concerns, are still insufficient. We have major shortcomings even in the CMIP6 generation of these models in important parts of the ocean, the western boundary currents, subtropical upwelling zones, and the Southern Ocean. And just for illustration, a recent paper by Hewitt et al. In Nature Climate Change gives an illustration about the filigrane structure of the Antarctic circumpolar current and how our models with the resolutions do in this sense. 100-kilometer resolution isn't really picking up any of the turbulent fluid in the Southern Ocean. 25 kilometers starts to show eddies. 8 kilometers, a much richer structure, but it's only at about the kilometer scale that the real structure of ocean eddies start to show up and take effect in the circulation. The same obviously holds for atmospheric model. Here, just cloud cover fraction compared from a 50-kilometer resolution to a 2-kilometer resolution. And clearly, resolution needs to be increased, but I fully agree with David. That's only one of several options to make progress in our understanding and also our delivery of policy and public relevant results from climate science. And here we come to high impact, low likelihood, and high risk processes. This gives you in this little picture just a wider perspective of what we are talking about. We're essentially talking about unexpected events, surprises, compound events, cascades, but also unexpected human actions and the classical climate tipping points. I think we also need to really take a focus on the impacts of the changes that we're talking about. And here we have tried to illustrate that in a very simple depiction here, where we plot the speed of forcing versus the speed of the response of the climate system. And that's usually sort of in the world where we talk about tipping and a highly damped system. If you then, on the other hand, look at the level of impact, which is relevant for local people and ecosystems, then we're talking of low level of forcing and yet high level of impact, which would be these hill events, or high level of forcing at the other extreme and low level of impact, an extremely resilient system. Obviously, in the climate system, all of these things are present and they need to be represented in our models. And that's why it's so important that WCRP has installed the Safe Landing Climates as one of the Lighthouse activities. They are very active. Workshop in Geneva is impending in a few days on the high-risk cascading shocks. Gabi Hegel is here part of the steering committee. I believe she's even a chair of the steering committee. And there's also the second edition of the Global Tipping Point Conference in Exeter that I would like to draw your attention to coming June 2025. More immediately, we have a little group under the leadership of Gabi Hegel, who is preparing a review paper on high impact climate events that should also encompass tipping points. And we are in the process of scoping that paper that should actually be also an input to any activity that IPCC is developing in terms of assessment in its 7th cycle. And that brings me back to IPCC, because I think it's really an important lever that we have as a wider climate scientific community. I mentioned the scoping meeting, and certainly why is important this consensus. Just a little thought experiment. Imagine we had no consensus on radiative forcing, no consensus on climate sensitivity, or no consensus on detection and attribution. These are all key pillars of the ultimate findings of IPCC, and therefore the scientific basis, for example, for the Paris Agreement. And so consensus, as surely many have also personally experienced, is also driving science forward, because you sit down with people who do not agree on what you claim initially, perhaps on an incomplete set of scientific findings. You debate, you try to understand what the reasons of divergence are. And certainly in these 3 topics that I've mentioned, scientific consensus is not fully there. There is always room for improvement. Climate sensitivity is the case in point. But nevertheless, we do not have camps in the scientific community that still claim equilibrium climate sensitivity is less than 1 degree, or even higher than 6 degrees. So there is a minimum consensus here on which we can build. And therefore, I believe that hill events, tipping points, impacts, loss and damage that are caused by those would be very useful to have a consensus in the next cycle. Unfortunately, the opportunity of a special report cannot be realized, and so we have to hark back on the possibility of chapters in each of the working group reports. Why a chapter? The chapter ensures that you have a sufficiently large number of colleagues who are interested in this very topic. And this is really in difference to the 6th assessment report cycle, where you could arguably say tipping points has been addressed to the extent possible. But in the end of the report, it was scattered among many different chapters and addressed in these chapters perhaps by a contributing author only. And the real debate of consensus finding that takes place during the assessment work that covers about 4 years for every cycle could not be done. A chapter would be an opportunity to do this in working group 1, in working group 2, and in working group 3. And with that, I close, and I'm very much looking forward to questions, comments, and exchange with all of you. Thank you very much.
Thank you very much, Thomas. We have so questions are starting to pop up in the chat in the moment, particularly many for David. But I think it would be good to hear the views of both speakers on the first question, for example, which is quite liked by the audience, from Daniel, for what is the relationship between prediction and risk assessment? So we, you could argue, and I think he's referring to David King, that what we really want is a risk assessment and not necessarily a prediction. So maybe this is a good one for both speakers, but let's start with David.
Yeah, thanks, Gabby. Thanks, Daniel. So I think risk assessments and predictions are intrinsically linked. When we think about climate predictions, they are also intrinsically probabilistic. It's in the nature of the system that even if we had a perfect model, or many duplicate models, we are only ever talking about a probabilistic style prediction. And Thomas's lovely plot, which I hadn't seen, about an initial condition ensemble AMOC response, it illustrates that so clearly that you may understand the world perfectly, you may know exactly what your climate policy is going to be, and there will still be potentially very large uncertainties to quite what will happen, and they may have odd characters, as in you might have a bimodal setup, as Thomas was showing. Prediction is about grasping that, and that is a crucial thing to do for us to understand what our risks are. So I think there has been a big move in policy circles and in industrial circles, say, actually, we want you to tell us about risk. And that's fine, because it brings in other things. It brings in vulnerability, it brings in how we invest in our systems, it raises questions about how you build resilience, which are really important. But I do worry when I speak to colleagues in social science settings that they see this as a question of building resilience, and they haven't really grasped the huge uncertainties, the level of uncertainty that there is in some of the physical aspects of the system. So I think there's a danger in focusing too much on practical risks and ignoring some of the information that we have about climate predictions. Yeah, I'll maybe hand over to Thomas on that.
Well, yeah, just very quickly, I think that's why it's so important to have good regional resolution. And I'm not certainly solely pushing kilometer scale global models. I think, in fact, a key word that has not been expressed so far is the use of a hierarchy of models. Because that really brings to the question, when is a model good enough? Well, ask the two Nobel laureates of the Nobel Prize in Physics in 2021 whether they considered their model good enough. It's the art of modeling that allows us to draw conclusions with even imperfect models. And I think we are today very much in the same situation as these esteemed colleagues were 50 years ago. They had to, in fact, wonder, how far can I go in interpreting my model? And that's the real crucial question. How far can we go today in interpreting our models in terms of regional climate change, and ultimately also in terms of the risks? And the simulations that I showed by Natasa Romanu is really a case in point that we cannot trust the models just because 100 models show the same thing. The 101st simulation may actually show something else. And that's where the science has to kick in and ask the question, what is happening there? Sort of a similar question. Why is it that we had this ocean heat wave starting in 2023 with anomalous temperatures at a scale from 60 south to 60 north in the entire global ocean. That was an unpredicted event with unknown consequences still.
Can I just jump in a little bit? Because I agree entirely with everything Thomas has just said. But this aspect of what Hasselmann and Manabe were doing is sort of, is their model right? I don't think they would even think about that because they're not using it that way. And we're in the same situation today, except the urgency of climate change means that we have all these different disciplines together. And so we get things like the IPCC Atlas, which on the one hand is a fantastic tool, but on the other hand encourages misinterpretation because different disciplines come and say, okay, what is happening here? And they can go and get an answer. But actually the people who generated that information wouldn't necessarily think that was an answer.
Yeah. You remember the long discussions we had in AR5 when we started with this Atlas. They were endless. I also agree with you. It's a fantastic tool, but you still need to think when you use the tool.
Yeah.
We have a question that has been asked by more than one person. So now I'm trying to find the questions again. So one of them was David Lawrence, but there was also I think Heiko Gölzer wants to know actually what is a consensus on tipping points. What do you mean when you say consensus? Do you mean you know exactly when it's going to tip? David put a slightly different spin. How confident are you that there's actually consensus to be achieved? Because the complexity and uncertainty of that topic may not be straightforward to achieve consensus. So it would be good to hear from Thomas first, but also I think this would be interesting to hear what David has to say about it.
Well, thank you very much. That is an extremely pertinent question. What is a consensus? When is a consensus reached? I think the essence of consensus is not really the final formulation. It's the fact that we sit down and we think very hard, what can we say that is robust and that is based on multiple lines of independent evidence. And with independent evidence, I mean, for example, different models of different resolution or of different pedigree, but also observations or simply theoretical understanding. And the consensus then crystallizes out where it can say, well, for example, Pine Island Glacier seems to be an unstable system. We have evidence not only from current observations, but also from paleo circumstantial evidence and from high resolution coupled ocean ice sheet modeling that allows us to say, yes, here is a system that is prone to tipping, but here are the uncertainties. And the uncertainties are because of these and these reasons. That's sort of what I understand as a consensus. The consensus to ask in the topic of tipping point for a consensus that would say AMOC is not a tipping point, but Pine Island Glacier is a tipping point. I don't think that consensus will ever exist, but the consensus is much more detailed in the sense that we talk about a component, about an element, we try to understand it, and we know what the reasons and the sources of uncertainties are. And that's sort of laid down in a document where we are in consensus with the points that are in this document.
Yeah, I would agree with everything there. I think the role of consensus is about bringing together our understanding from different parts of our disciplines and from different disciplines so that we can see it all in one place. And I think this is so important. I think given the complexity of climate change, of understanding climate change, of the climate system, but also of the economic and social systems and how they come together. There are so many different people with so many different perspectives, and consensus is about bringing that together so that we can have a conversation which is not talking past each other, but talking with each other.
Thank you. So just to drill a little bit deeper, what do you think is the role of process understanding and making the models more detailed to ensure that they replicate what we think might contribute to tipping, and what is the role of observations here, which we really don't have other than paleoclimate? Would you like to add a little bit more?
Was that for me? So
Sorry.
Go ahead,
is that for me
David.
or for Thomas?
Yeah,
Go ahead, David.
I wasn't quite sure of the question. I think for me. So for me, I see the last 25 years as a period when there's been huge, where climate science has spent an awful lot of time developing models, and the emphasis on the modeling has been greater than it should have been. And I see value in something of a rebalance on a focus on process understanding in reality. Now, the models are a tool for that. So when I was arguing about the problems of investing so much money in high resolution models, the high resolution models, things like Eve, the justifications for that have been made on the basis that they will give better predictions. I don't think that's a sound argument. But there are reasons for saying a high resolution model will represent certain processes better and help us understand them better. And through that understanding will give us better communication of things that we need to know. But that subtle difference in argument is really important, because if you're just trying to understand certain aspects, you don't necessarily need to have a representation of the whole climate system. You can focus in on things. Whereas if you're trying to just predict the future, then you have to have everything. And it would be really helpful, I think, to focus on that process understanding. So Gabby, I don't know if that was quite answering your question, but I think that emphasis on process understanding. And when we say process, I don't just mean the physics. The social systems and the way societies behave and the economics come in here too.
Right. Well, just to add a little element here, we talked a lot about IPCC. I think the process of IPCC, the cyclicity is also responsible for quite a substantial pressure on the modeling centers to present at every cycle a new model or a new model family that has been applied to new scenarios. And I've said for several years that I think a staggered approach would actually take off a lot of pressure of the scientific community and free the scientific community to think more about a specific model generation. And that's essentially what you are calling for, David. So just figure that every odd cycle would be allowed to come up with a new set of scenarios and storylines for scenarios. This would be the work of the social scientists and the economists foremost, and the integrated assessment modelers. So they would be put online every second assessment cycle. Every even cycle, the modeling centers are allowed to enter new models with higher resolution, with more climate system components coupled to them. And that would immediately free a lot of resources and reduce a lot of pressure. But I don't see any thinking process that would actually lead to such a decision. Because there are other forces as well who want to see a constant competition in better and better models. But, AR6 is a point in case where high climate sensitivities all of a sudden popped up as a surprise. Nobody had time actually to think about it. And I'm sure one can learn a lot by analyzing high sensitivity models. And then perhaps decide, okay, there's a missing process in the radiative balance in the atmosphere or in the coupling to a system that we need to address. And that would then be sort of the learning curve that you could take if you had more time and have a more relaxed schedule of scenario development staggered with model development.
Thank you. This is leading us very naturally over to a question from Raphael and Rake, but also a counter question, or a question that is closely related, from Joshua. So Rake and Raphael ask, since we have only one measurement of realization, don't we need a very and of a very chaotic climate, don't we need a lot of ensembles to sample its attractor and figure out what really agrees with the observation? So don't we need large ensembles? Whereas Joshua asked at the board, asked them a different question, which is, given how expensive climate change is going to be, shouldn't we have the money to have these very, very high resolution model simulations, which is a question that is often in tension. Who would like to start?
I'll dive in. I'll dive in on those because I love those. So this point about do we need large ensembles in order to explore the climate attractor, or actually yes, let's just say climate attractor. It's not quite clear whether it's attractor or pullback attractor or all sorts of other things, but let's not go there. Let's just say climate attractor. Yes. It's one of those things that really strikes me that one of the problems of building the very high resolution models, a model that fills your computer, if you can then only run it a handful of times, you don't even know what happens in your model. You can't quantify climate change in your model because you haven't got the ensembles necessary to make that quantification. So we need to have larger ensembles, but we also need to have a lot more thought about how we design those ensembles. The sensitivity to initial conditions in that sort of typical butterfly effect way, that's one element of it. But there are other elements of it in terms of what happens if the whole strength of your North Atlantic circulation pattern at the start was different. Then actually you can fall into a different set of trajectories going forward. So your sort of large-scale initial conditions can affect this, as well as, of course, model error, model versions, and all sorts of things. So there's a whole issue of needing larger ensembles, needing more effort in designing those ensembles so that we can understand even climate change within a model. And just to flag the second point, Gabby, I can't remember who asked the question, but given the costs that climate change will impact on society, the argument is made, given those costs are so huge, surely this spending on high resolution models is worthwhile. I think that's not a sensible argument in itself. Is that the costs of climate change for society are so huge that I do think it's worth spending a lot of money, a CERN type activity, that sort of investment, or I can't remember, that sort of investment is worthwhile to understand what sort of threats we face, what sort of risks we face. But that's far from saying, therefore, we need the K-scale models. There are lots of different approaches to this, and we need to be bringing the community together to address those different approaches. But I'm all for spending billions on this problem. Sorry, I was keen on that, but Thomas, I wanted to.
No, I think that's comprehensive what you just said.
I have a question for David that has been sitting there for a little bit, and it was also a question that I asked myself. So you mentioned the possibility, David, to use the models as a tool for understanding, and then instead of using storylines, use something, instead of using predictions, use something like storylines. But how can you convert insights into something that informs the future? What is then your method? And isn't it even less safe to just rely on our limited imagination rather than throwing masses of climate models at it?
Well, fundamentally, I think, Gabby, I just completely disagree with that. I think the points that I'm raising about we haven't addressed even how you would quantify climate change within a single model. We haven't addressed how you would quantify the space of possible models and therefore what they can show. That modeling world just provides the ruse, the misleading idea that we have more information that we have. Actually, investing in people, investing in expertise and researchers who understand these different elements of the system and different processes, and then getting that's the key. It's investing in expertise. But what you then really have, and I feel painfully strongly about this, is that nobody can understand all these different aspects. So this is what your model does. Your model brings it all together, but your model has all these flaws anyway. So we do need to invest in expertise, but we also need to invest in getting these different realms of expertise to be talking to each other, not just passing data from one to another, but passing perspectives and tools and ways of addressing problems. And that's how we integrate these different levels of understanding. And I know the IPCC has been mentioned a lot here, and the IPCC is great and does a fantastic job in a number of these things. Nevertheless, when I look at universities and research establishments, certainly in the UK, and I'm pretty sure in America and in Europe too, you are rewarded for specialization. And we need people with deep knowledge. We need specialization, but really it's 2 or 3 down the list before you get rewarded for working across disciplines. And climate change is a multidisciplinary problem. The incentive structures within our research establishments are principally failing in our ability to draw these the themes together and provide better predictions. Sorry, I seem to have become animated. I'm sorry.
I think on that last point, I think good examples of where you can actually influence that reward system is efforts like the Grantham Institute, to which you are part, or here at the University of Bern, the Oeschger Center, where our mandate is to work in an interdisciplinary manner. And I think more and more these centers will pop up. But it's up to the centers to essentially define their reward systems, because the administrators in the universities do not yet have the experience how to go about with these interdisciplinary centers. So it's a little bit our task here to be creative.
And it's also the funding system. I remember a painful interview where I was grilled on the interdisciplinary part of my proposal, and I couldn't give the detail that the reviewers considered necessary in that context, because it was interdisciplinary, as David said. So we have to really think about how we deal with the problem that we reward people for working across disciplines and learning about other disciplines, and trying to talk to each other also in a way that we understand what they're really saying and why they do things the way they do them. So it's an interesting question. To go to research community, there's also been a question from Shaoria, who is an early career researcher, and he's now hopped, the tool is now hopped away, and would like to know, as an early career researcher, how what would be your thoughts on how to on where to focus their journey on climate modeling, and what areas would be suitable for a newcomer to address the research gap? Maybe that's a nice one to a more positive one. Who wants to start with that one?
Well, my first answer, which may not be very helpful, but I think I still give it. Do whatever you feel the fire is burning for. You need to have passion for what you're doing, then you're doing fine. And you pick your advisors, groups that are working in the areas that you are interested. Check them out. See how open they are for new ideas, because the ideas will not come before you start in the new workplace. The ideas arise when you engage in discussions with the colleagues that you find at the place that you work. So look for look for a sizable group, but a group that is not too big, where all the office doors are closed, but an open environment that is engaging and that has the network also to bring you further once you have done your PhD or your postdoc, that the network helps you to move forward and realize the options that you have created during your previous work.
Excellent answers. I think passion is an interest, and fun is the answer. David?
Yeah, so very much agree with that. Go with what you're really interested in. But beyond that, I would refer to what we were just discussing. I think, for me at least, the really exciting areas are those cross-disciplinary areas. They're in the connections between different disciplines, and that might be maths and physics, or it might be the cryosphere and ocean. It's which might seem very similar, or it might be economics and the ocean. It's sort of it go in directions that take you across these different disciplines. And as I was saying earlier, there are places where that opportunity is cropping up. But I also think it will just develop more broadly. I don't think the system supports it well at the moment, but I think there is also an acknowledgement that it doesn't, and I think it will improve. So as an early career researcher, I think it's still a good place to go.
Yes, I agree. It takes a while, so it needs patience for interdisciplinary stuff. It takes a while to understand each other and move over from a hand me the data and I'll deal with it, a mindset, to let's understand this together, which is much fun.
And don't forget to drill deep, at least somewhere.
Yes.
Because that really creates authority. It doesn't really matter whether it's precisely that topic on which you will be working in 5 years or so, but if you ever have drilled deep, people will know it, and that's sort of part of building the authority in the scientific field, be it in economics or in biology or in climate science or in cryospheric modeling or wherever, but drill deep somewhere.
Excellent addition.
Absolutely.
We have a kind of slightly different topic raised by Gerd, and I forgot to sometimes give the names of the question askers, and I apologize for that, but this one is from Gerd. He would like to know to what extent AI might be taking on, might be helping us to get better climate predictions, for example, for high resolution modeling, and breaching scales and so on. So that was directed at David, but I think it's again relevant for both speakers. So what do you see also the role of AI in, for example, identifying possible tipping points and also improving our whatever we mean by predictions? Who wants to start?
I can start. I'll probably leave the identifying tipping points to Thomas. But I will. But I'll start, because I do get asked about this quite a lot, sort of since my book. So, and there is quite a strong and lively debate on this topic at the moment, and I, like many people I speak to, have strong feelings about it. I think I'm really very worried about the assumption that AI can take the role in climate predictions that it's starting to take in weather predictions. In weather predictions, there's good reason to think that AI would do a good job if you designed it well, essentially because the information is in the training data set. So so you'd expect that to be good, and they are doing fantastic jobs. But a lot of people are jumping on that and saying, oh yeah, so now we can apply this to climate. And I just don't think you can. I think the slow processes in climate and the hidden processes mean that the information is simply not in the training data set, and you will mislead ourselves and society if we just go down this route of AI-based climate predictions. It's a very bad way to go. On the other hand, I think AI has actually a very powerful tool in building better models, in potentially in terms of replacing certain parameterization schemes, or building better parameterization schemes, representing some of the fast processes where the data does contain the information. It may well help us build better models much more quickly, as long as we don't think it can do the whole job.
Yeah, I think AI will be a tool that doesn't go away, but it's also not the panacea that will solve everything before we start thinking. So creative thinking, interpretation of data, I see AI as a tool to help us identify, for example, patterns. Certainly, as David said, for weather prediction, if you're only interested in weather phenomena that have happened in the past, it's fine. I wonder, and I'm sure somebody has started already that investigation, the terrible flooding, the tragic accident and event that happened in Valencia just the other days. I wonder whether AI, based on the training set of past, meteorological situations, would have predicted that. I don't know. But I suspect, because that has been an unprecedented, unrecorded event so far, AI probably wouldn't have identified it. But I don't know. I don't know. That's the open question. And, tipping point and hail events are great examples where perhaps AI will also say, okay, I asked AI, give me the question, AI asks AI.
Yes, I think that's a really good point that you both raise, is that you basically are trying to go out of samples and you cannot get, and with our models, we have probably we have some limitations in skill and what they can actually do, but there's at least physics or some ideas of how this works behind it, whereas AI is extrapolating the data in a really, really powerful way. But it's really interesting to also raise this point of the floods in Valencia and Barcelona, because it also identifies how important it is to work across from physical science that predicted that event, and it did actually predict it, I think, reasonably well. I got warnings on Twitter beforehand that this would be a very impactful rainfall event, yet the societal reaction was the event was so surprising for society that they didn't react well, and this is something that is also a thread with the Ahrtal floods in Germany, for example, where the problem was not that it wasn't forecasted, but that the response to it in a society that hadn't experienced anything like this before was not sufficient, and so this raises the question: how do we go about publicizing and informing society? And now we have we have another question that is from Simona, who agrees on the question of the interdisciplinary science. As an interdisciplinary scientist herself, or himself, we need to investigate. So they challenge us. We don't need more modelers and to delegate storylines to social scientists, but we need a different mentality spearheaded by climate modelers and I can't really quite understand what the question expresses. So I've been staring at this for a while. So what do
Are you on the Simona Petty's question?
Yes, I'm trying to understand the question. Maybe you guys have a take on it.
Well, I think this comes. I think Simona is right. Is this we have this problem that Earth system models, the big complex models, take a huge amount of effort to build and to run and to keep running as they keep changing. So there's a lot of investment there. I'm not saying that's necessarily wrong, but it means that the community, the research community, is somewhat skewed towards people who have familiarity with models, because you need to put in that investment into those people in order to have the models at all. But it does mean, and I think this is what Simona is getting at, that the non-model based approaches, or where the focus is not on models, tend to, I'm not quite sure how they say it, but they tend to be sort of downgraded. These aren't seen as equal inputs into the discussion. I think maybe that is what they're saying. I'm not sure whether that's quite true, but I do think there's that sense of it's, well, Gabby, earlier you were mentioned the problem of funding multidisciplinarity. Yeah. This is kind of an element of that it's seen as fringe.
Well, I perhaps do not fully agree with the sort of the suggested conclusion of that question that major funding goes to climate modelers, because if you come back to the question, how do big modeling centers invest their computer time? And the computer time is limited to 24 hours a day, essentially, if the computer isn't down. It is the new storylines that dictate for the next IPCC or whatever assessment, even a national assessment cycle, what fraction of CPU is dedicated to that question. And it's the storylines ultimately that generate that need for computing. And so we need to be very careful what we're talking about. Is it research funding of people who develop models, or is it sort of implied expenses through computations that you need to do in order to be part of the next overview figure of projections? And so I think there is no way around generating platforms where those interested in devising storylines, and in devising storylines, you need economists, you need social scientists with their expertise, with their view on how societies can evolve or do evolve at different speeds in different regions, different development, and sit together with modelers. I'm not sure whether modelers have the scientific capability to spearhead scenario development, unless you want to go back to the very clear scenarios, for example, of 1% per year increase in greenhouse gas concentrations, which are very good scenarios. We learned a lot from them, but they're certainly not good scenarios to get model results and then tell stories what the consequences of the climate change is, because that's a narrative too. You have the narrative of the scenario, and you have the narrative that is informed by the model results at the end.
Thank you. And that has brought us naturally to a question from Kubik on given the nonlinear nature of the climate system and deep uncertainties, how essential and how useful do you think are these coordinated model simulations to get a consensus on tipping points? And that could also be useful for considering when designing tip map and so on. So how do you go about using, or are they useful, and how can we make them more useful?
Well, MIPs are certainly useful. One may question whether every single aspect of the climate system needs a MIP, but I think TIPMIP is really occupying a special place here, because it's focusing on these surprises that may occur in individual simulations. That's why I put that little figure in of Natosa's paper. It's important when you do MIPS to go beyond the classical approach of already designing consensus figures by showing all the plots. The interesting thing really is, where do the models deviate from one another in a fundamental way? Where are bifurcations, for example? Where are different attractors visited? Where are regions where a completely different behavior is observed in model simulations, even though on a global scale metric, they would not be different. Things like that, I think, can only be looked at in a community effort that is gathered around a MIP.
Yeah, so I strongly agree. I think the MIPs are useful. I perhaps worry that we might have too many. I think there's a sort of, it would be useful to gain more consensus about what are the important MIPs to have. But tip MIP I think will be a very valuable one, because I don't think that is something that is being done terribly much elsewhere. So I think that's really valuable. In the original question of sort of what's the value of consensus, as Thomas was saying, it's kind of the opposite. What you want to do is find out how differently models can behave, and while still being some sort of credible representations of the system. And again, there's a design issue there. The MIPs are good for that and very valuable, but we're looking for diversity. And again, there would be value in getting communities together to have some consensus about how you explore diversity, how you explore model space. Yeah, sort of laying those foundations of what is the goal of a big complex model like an Earth system model for understanding these processes in reality. I think we do have something missing there, but the MIPs are really important. And that kind of goes back to what I was saying. My anti the high resolution models at the start comes from the idea of, if you put all your investment into a very high resolution model, that tends to push out the ability to make multiple different models, and what you learn, and I think you learn more from difference.
Yes, which raises back to your question, what model is too bad to be informative?
Yeah.
I don't think we really know the answer to that yet. There was also a question from Chris Bernard earlier on, that how to get are we making sure that we have a good involvement of the developing global south and developing countries in the tipping point assessment paper, and we are very keen on that. So any suggestions are very, very welcome. Email me or email any of us. And I think we are now 3 minutes out. There's a question from Amane that we could try to answer in 3 minutes, or we could just give up. So the question is, so we should keep it very, very brief. Your talk is mainly about constructing physical understanding. However, but is there a role for data assimilation when looking at tipping points? Do you have views on this?
Clear yes. The question is, do we have enough data? But I'm very convinced that data assimilation and data analysis with a view of identifying approaches to tipping points is key. Just think of the AMOC example again, unfortunately, always the same example, but here we have the rapid array, we have the OSNAP array, which is much shorter, but these are multi-year efforts, and hopefully the funding will continue, because it's essentially monitoring the climate system at these choke points. It's costly, but I think it's worth the investment. Do not forget monitoring the critical points around Antarctica, Pine Island Glacier, Thwaites Glacier, etc. Doesn't mean you have to spend billions of dollars, but science can help to tell you where a good observation network or a super site, that's sort of the key word, is worth installing to monitor.
And it can be used to sample very rare events by poking your model in that direction with particle filters or things like that. So I think there's definitely a role for cool modeling tools.
I think that data assimilation is valuable, but particularly on tipping points. In fact, for climate prediction more generally, tends not to be, but it's the tipping points is where it gains traction. But it does then force us, or should force us, back into considering the issues of model error, and so those sort of differences in temperatures and it's in all sorts of other variables too. How should that data assimilation go? It's not clear that the same sort of tools that are used in weather forecasting are necessarily the right tools for this sort of event. So there's a lot of research to be done there, I think.
Thank you so much. I think we have totally run out of time now. So thanks very much for the to both speakers, and thanks to the audience. We have there will be more tipping point seminars, and it will be posted in due course on the website. And thanks so much for these excellent and thought-stimulating presentations and the way you answered the questions very effectively. Thank you.
Thank you very much, everybody.
Thanks, everybody.
Bye-bye. Thank you very much.
Bye for today.